Welcome, everyone. I think everything is now set up. So if somebody on Zoom or YouTube could tell me if they can hear me, because I think in the room this time it's really loud, or is it just me? Is it just more
Yeah, we can hear you.
Oh, not me? It's loud enough? Okay, good. Well, then it just sounds more loud. I mean, from my loud and clear I hear it on Zoom. That is very good. Okay, then we can get started. This is very nice. This is the first week now lecturing EML that the setup here did not change. So and I can also start pretty much on time, right? I timed it perfectly. But, perhaps in a few years, maybe I can do this in my sleep. Right now, it's still very exciting. Good. Welcome to the fourth lecture, in which we will be discussing at one moment classification, but I'm going to start pretty much where we left off last week, because we have a tiny little bit of linear regression or something related to it left, and it will make the perfect bridge into the topic of classification. You will see how and why. So let me make sure that the focus is here. Yeah, so where are we? We're now in chapter 3.5 of the ISLR book, and we're going to be comparing the k-nearest neighbor regressor to the linear one that we've been studying in the last 2 weeks, and you now know in and out. We were supposed to discuss the k-nearest neighbor classifier in the first lecture, but because of all the excitement in the equipment, I didn't get to it. And we were discussing this afterwards, because I think 2 times k-nearest neighbors makes a lot of sense. Except that you don't know what is the k-nearest neighbor classifier nor the regressor. This is pretty much the simplest classification or regression model that you could think of. Namely, I ask of you, what would you give as the regression value for x is 3? And what you do, you simply now look in the data, the training data you have, and you find the k points closest to the query one, right? And k is a parameter, so we ask the expert because they know, right? And as we established last week. If you set k to 1, then your task will be in the training data to find that point, that single point that is closest. And what you will then do as the output that you give to me back, you give the value of y, of the target attribute, well, corresponding to the k-nearest neighbor. Easy peasy, right? If we set k a little bit higher, if we set it to 3, 5, 9, or whatnot, right? I mean, you can also choose even numbers, but I'll leave it as an exercise for the interested audience member why this is typically not done. You just average the output values that you get for those k query points. Now, under the hood, when I say find the k nearest neighbors, there is one little problem that the book does not directly address. We need to somehow establish what is near and what is far. And that may seem simple, right? I mean, if we just have numbers, right? If we have, let's say, 1, and then we have 2, and we have 3, and you want to find the closest number to 1.9, hey, that's 2. Yeah, if we assume linear Euclidean space, could be nonlinear for all we care, right? Maybe somehow we find 1/10 up. Maybe this is harder than 9 notches down. Could be, but I'm going to let that slide for now, right? We just live in a happy world where we just use Euclidean distances and we can trust the measures that we have. In that setup, I mean, similarities are not a problem, and it's just a matter of measuring, and that's that. Okay, so Frank on Zoom. Yeah, I mean, I'm afraid I cannot adjust the distance to my mouth. I can try to increase the volume, but if you go deaf, right? I mean, then it's Frank's fault. Okay. Just shout no, no. And then I can go to this level. I mean, otherwise, I think it goes really above and beyond. I mean, Frank, is this a little bit better? Okay, well, David answers it's perfect. So they must be in league with each other, these students. Terrific, terrific, good. Okay, then that problem is now solved. So back to the k-nearest neighbor regressor. Distances are not a problem anymore, but we're just gonna wish away that problem. How do we set k? Well, let's also go a little bit back, even though this is lecture 3.5, to the very first lecture, right? Bias and variance. So what would happen if we set k particularly low, like 1, as we hear of an example, right? That gives, in practice, a relatively complex model. You use each and every of the data points you have just once for that particular value, right? So what you get, if you were to plot it, you get this sort of staircase diagram that you see here on the slide, because every training point essentially defines an area around it all of this actually the same distances, where it will output exactly the value of the training point, right? That's what the k nearest neighbor classifier regressor essentially does. It finds an area in which it will just give a constant output, right? Hence you get this 3D staircase. Naturally, if we use every individual data point to define one area for the output, we get the staircase, but it's in a way, well, overly complex, right? We have a very high chance of overfitting, and just to link it back to the first lecture, we have a very high variance in the model. If I change one of the training points, we get a very different output model for that particular area, right? There's no smoothing. Okay, that's not good. Let's increase k. Let's just push it to the max. Now, for a large k, we get a nice smooth or relatively smooth landscape, as you can see here, right? I mean, this is sort of like more of a wave, I mean, and this might actually fit the underlying function of the data quite well. Okay, what is now too simple? What is too complex? We'll get to that in a second. If we push k too high, let's say we set k to the number of data points we have, what would that mean? Well, then the output that we ask if we query is going to be the average of all the training points. So it's going to be constant for any point that we query. So essentially, rather than having a staircase, a step for each and every data point, we would just have one big step. That's the other extreme. Now, if you're somewhere in the middle, then you get something like this. It's somewhat smoothish, and it may actually be quite good. Back to bias and variance. The higher we set k, well, the lower the variance becomes, because the lower the influence of individual data points, but yeah, the more we increase the bias, right? Because the model becomes more and more rigid, right? I mean, if we set k to n, then essentially the output will just be the average. And if the only model that you're allowed to fit is the average, then of course you have a very high bias, right? Unless your data is completely flat, you will not be able to capture any real structure in your data. Good. Yeah, how do we find the optimal k? Next week or the week after. Let's first look at when is this type of regressor a good idea and when is it not. We've just learned a lot about linear regressors, linear models, and we know that they're particularly good when there is a straight line in your data, right? Or there's a plane in your data if we're looking at the multivariate case. Now, let's compare these two. We have these training points, which actually are sampled from a linear model, right? I mean, with some noise. And if we now set k to 1, we get the squiggly line, blue squiggly line. And if we compare this to the true relationship, this is, well, suboptimal, let's say. Now, if we set k a little bit higher, we set it to 9, just a number that was taken out of the big hat for where to draw your parameters from, you see that actually it starts to, well, get much more closely around the true line, right? So 9 is a pretty decent value here. But if we now compare this to what is the optimal linear model based on this training data, that's this line. It's an even better. So k nearest neighbor models are not that great when the data is actually truly linear, because it just wants to follow each individual points, right? And it has the tendency to hence follow too much, let's say, local structure, noise, potentially noisy structures in your data. Whereas a linear model has a very high bias, right? Can only fit linear models, nothing else. Well, obviously it shrugs this problem off. Right? Schmoish. Now, for this particular data set, if we now quickly look at, if we change the value of k from 1, which is all the way at the right-hand side, right? I mean, so the axis is 1 over k. That allows me to plot things. Wait a second. Okay, yeah, so I think, yes, so in Zoom, it again has audio problems. Yeah, I'm afraid I cannot really solve this problem. I can try to get, because I also hear the audio fluctuate a little bit. But if I do this too much, then it will start to bounce around. The only thing I can do to get the noise down is to lower the volume, but then you can't hear me anymore. So I'm not sure what is now optimal. But let's try for the next minute or so, and then give me feedback on whether what we're currently doing works. And otherwise, well, we'll try to adjust a few of the knobs again. Okay, good. In the worst case, I can do this. Oh, but that is okay. The microphone just works weird, I get the impression, right? Is it also for you guys fluctuate, or is it just the reverb that I get here? I really have no idea what to do about that. And where's the, because it should then somehow have some feedback. I'm afraid I can't do anything. So, okay, let's just continue. On the right-hand side, I have, in a normalized scale, 1 is essentially k is 1, and on the left-hand side, I have then k is many, right? Number of data points that we have to begin with. Okay, and as you can see, the green line is going down if we crank k up, right? If we go more to the left-hand side, but it never really truly achieves the same mean squared error as we can with the linear model. It's the dashed line. Not the true model, that's linear model. So for linear data, KNN kind of sucks. Now, if we have data that is not linear, then, so it's mildly nonlinear, as we call it here, it has a little bit of this S shape, then you get the following. So for 1 and n, I mean, it gets a very jittery type of pattern, right? I mean, you don't want to use 1 and n. You never really want to use 1 and n, because that's just giving back training points. But the red line starts to hug the true black line here quite well, right? So for nonlinear data, KNN seems to do quite reasonably. And again, if we now look at the errors, the mean squared errors for different values of k, you see that if we if we have actually a relatively high value of k, we achieve a better error than with a linear model. That's neat, right? That's neat. So for mildly nonlinear data, KNN is already better than linear. So why did I bother to teach you linear methods? Well, we'll get back to those in a minute. But first, I'm going to continue bashing them a little bit. Let's make the data even more nonlinear. And as you can see, I mean, the red line is again doing very, very well. In blue line, too jittery, 1 and n. Friends do not let friends use 1 and n. But for 9 and n, 3 and n actually looks quite smooth. And if we now look at the errors, the mean squared errors, perfect, right? Much, much better than a linear model. Now note that what are we doing here? We're just sampling a few points from our data. We're almost not infusing any information about, well, how we think the world operates. The only thing that we're infusing is, well, k, right? And k essentially is a smoothing parameter. We're looking here for these values at a highly non-parametric model, right? So with a very low bias. It follows the data very strongly. And the mechanism that we have to not make it too variable is to crank up k a bit away from 1, right? Then it's too variable, but for reasonable values, we have a method that is low bias. I can actually do quite well. There is a problem though, and there's a reason why we don't use KNN all the time. I already said that we swept under the rug that we need to measure, well, distances, right? How far away are different points? And if you just have one dimension and you make your assumption everything is Euclidean and linear and whatnot, okay, it's fine and dandy. But if I give you more and more and more dimensions, 1, 2, 3, 4, up till 9 or whatnot, in Euclidean space, distances start to become more and more meaningless, especially if not all the predictors that I give you are equally useful. So what we have here, I have a model where I think if I recall correctly, only the first variable is relevant. All others are completely random, completely independent of the target variable, right? On this data, if we would do multiple linear regression, we would just shrug and just learn coefficients for x1, and all the others would push to x to 0, right? It would not be a problem. KNN does not have that luxury. KNN will basically tell the data is important. Try to follow the shape of the data. And what it will do, it will measure distances, not just over x1, but also over x2, 3, 4, and so on and so forth. So what we have here, from left to right, we go for one predictor that is relevant, and then the comparison to linear model, you see that the green line dips below. Yeah, great, that's really cool. Then I give another attribute in addition, x2, that is irrelevant, and you see that the green line already creeps up a little bit, right? I mean, it becomes more difficult to measure these distances properly. I add another irrelevant variable, then we have the rightmost plot in the top row, and you see that all of a sudden, it does only as well as linear regression. And the moment I start to add more and more and more, the green line goes up, 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 and I mean quite extremely so already for 6 or 5 irrelevant additional predictors, right? I mean 1 relevant, 5 irrelevant ones. You can imagine that in many, many applications, we're not talking about just a mere 6 predictors, but we're talking about tens, hundreds, thousands. And beforehand, we do not know which of those are now truly important. So yeah, you don't want to just throw high-dimensional data at KNN because it suffers, as we call, very severely from the curse of dimensionality. Particularly because in high-dimensional data, it's really difficult to measure meaningfully how far 2 points are away from one another. Okay, question on Zoom. Would Euclidean norm also have a problem with logarithmically scaled data? It doesn't really have to do with norms or with scalings. It is the key problem is that if you have a high dimensional space, all distances tend to the same value. That is what the core of the heart of the problem is. And it doesn't really matter so much what the individual scales of the individual dimensions are. I would love to discuss this in greater length. And for another lecture that I teach, I have, well, 2 or 3 lectures, hours completely prepared for it. But in email, it goes a little bit too far. So I'm afraid I'll have to disappoint you maximum. It's nice that I can see the names, right, if people ask. But we can discuss this perhaps in the break or afterwards. Good. One other additional advantage of the linear models, and why we do love them, they do not suffer as much from this cursor dimensionality as KNN does. I say as much because in the end they do. I mean, any method does. I mean, that's more data is definitely not a blessing. It's mostly a curse. Linear models do give us the chance to compute p-values, which attributes, which predictors are significant, how certain are we of certain coefficients, and so on and so forth. Right? So for nonlinear data, they suck, and then KNN can be your friend if you have the right predictors. But if you're willing to make some assumptions of the model of your data, linear models, or it's similar class, where whatever assumptions you want to make, those will be your friend. Okay, good. This was it. This was last week's lecture. I mean, Kate, thanks, bye, and welcome to this new week. Where right now welcome to lecture 4. We're going to be talking about classification. Let's forget everything about regression, right? Let's talk about classification. What is classification? Classification is the other side of the medal in machine learning, in predictive data-driven methods. Whereas in regression, the target attribute that we're interested in predicting is continuous valued. It's numeric, right? Sometimes ordinal. In classification, we want to sort apples from oranges, right? It's a discrete task. It doesn't have to be strictly binary. It doesn't have to be just apples and oranges. We can also have pears and bananas and whatever your favorite fruit may be. We could practically have infinitely many classes, but these do not admit a strict ordering. That's the general idea. Otherwise, we're kind of back in regression, right? We really just want to say it's a this and it's not a that, rather than, hey, it's somewhere along a certain axis. So for example, the running example we'll be using for the next few slides is whether or not people are likely to, well, default. So defaulting is that you cannot pay back your debts. And one of the features that we were looking at as a predictor for whether people may or may not be able to pay back their debt is how much credit did they already draw on their credit card, right? So how much did they borrow already? Right? So, you can already imagine that people who have a lot of debt outstanding on their credit card, perhaps you should not give them too much more, right? But hey, perhaps there's a bit more subtlety to it. If you plot the data, it looks like this. And you can see indeed that people with a low balance, so with a relatively low credit draw, and with a particularly high income, actually income seems to be practically uninformative. They're all blue circles, and blue circles in this case is good. And the red pluses are the people who do not pay back, who default. And terminology is always a bit stupid. But okay, so those people we would like not to give any money to. Do we have to ensure that the classes are disjunct? Well, it depends a little bit on how you consider what is disjunct. I mean, it's a question that I just got on Zoom. Each object in the standard setup has only one label. I mean, it's either an apple or an orange, right? So in that sense, yes. However, just like with regression, we have a number of values, right, for our predictors, for x1 up till however many we have, and then one label. And it might well be that for exactly the same input vector, for exactly the same input values, we have a copy, and the one says apple, the other one says banana. That is possible, right? That means that it will be very hard to get 100% classification accuracy, quite naturally. So yeah, disjunct depends a little bit on how you define it. Good. Yeah, so what do we want to do? We want to predict categorical outputs. Yeah, so as examples, I mean, is a patient going to die or not? I mean, is a transaction fraudulent? I mean, should we give somebody a loan? I mean, you can, should we go left or right here, but in a self-driving car situation? This is classification in a nutshell, right? I mean, okay, everybody ready to go back into the time machine? Welcome to the first week of EML, where we're going to be talking about, well, a little bit about the introduction. What are the things that we're going to be doing in this lecture series? We're going to be talking about classification. Well, isn't that amazing? You already know what classification is now, right? I mean, that's 2 or 3 weeks ago you didn't. I'm sorry that if this comes across as a little bit confusing, but I try to at least cover all the things that we wanted to, that you at least get to hear it. Right? So you know already how to evaluate whether a regression model is any good or not, right? Mean squared error is our friend. In classification, well, there is not necessarily a mean, and hence we can't take a square of it, and then the error, okay, what is this even? So in classification, we typically just give points to whether the method got something right or not. And this we typically call a loss function that we apply to it, right? Or the misclassification error is one of the instantiations of it. So on the training set, what you typically do, you just take how many errors did you make, or how many things did you got accurate, depending on which of the two you're most interested in, which we just measure as a predicate P with the predicted value. Is it equal to the value that we actually wanted to have predicted? And well, that is that, right? And then the average error is just the average. Easy peasy. I could, in a way, already stop the entire session about classification after what I'm going to tell you next, because we know what is the optimal classifier. We can easily write it down. It's namely the base classifier. What is the base classifier? That's the one that assigns that class label that achieves the highest probability under the generating distribution. Right? So if we somehow magically, and this is kind of why I cannot stop the lecture just like that, if we magically have the true generating distribution, and I then simply look, okay, what is the probability that for this input that the generating distribution would have generated label 1, respectively label 2, whatever, right? The apples, the oranges, and so forth. And I simply take that one that it assigns the highest probability to. That's the best possible thing you can do. There's no beating the base classifier. Now, the tiny little problem is that we don't have the generating distribution. And that is then, in a nutshell, what all of classification is about. How can we get a fingernail behind that or get it into our hands somehow? Yeah, so for synthetic data, well, we have the generating distribution, right? Because, well, we generated data ourselves. I mean, we played a game what I call retarded squirrel. I mean, we hide a nut somewhere and we're like, oh look, a nut. So it is useful, this game, to see if your method actually does something reasonable, right? Because you know what the ground truth is, but you should not get too excited if your method solves. It can find the nut, because typically we are not so good in hiding the nuts, right? Nature is always more crazy than you can imagine. Truth is stranger than fiction, as they say. So here we have some data that we generated ourselves, 100 observations, 2 classes. We have ochre and yellowish circles, and we have blue circles. And I know exactly what the true generating function is. And the dashed line is now that line where the base optimal classifier says, like, I don't know, it's 50-50. It's exactly 50-50. Is it now blue or is it red? I don't know, right? And as a result, what we have here is that every point that we would query on the south side or to the right, to the bottom to the right of this dashed line, the base optimal classifier assigns a probability that is higher for blue than for yellow, and hence it spits out blue as the predicted answer, and on the top left side, okay, it would be yellow. Now, this dashed line is not just pretty to look at, but it also allows us, if knowing the optimal, so the generating model, what is now the optimal accuracy that you can possibly achieve, right? We know that this is the best possible classifier, you cannot beat it. And in this particular case, the nut that we essentially have hidden is this 0.1304. That is the best possible classification accuracy that you can get, right? So this is nice because now on this data, we can train other methods and we can see, okay, how close do we get to this optimum? And note that, well, just from a very naive perspective, 100% accuracy or 0 error would have been best. But yeah, is this even attainable? Right now, we know what is attainable, 0.1304. That is essentially the 100% respectively 0 error, right? Okay, now let's throw some k nearest neighbor at it. This is for k is 1, so we already know that this is very overfitty. I mean, it's way too varying. And as you can see, the black line, the solid black line, it is very, very squiggly. You can also see here that by k is 1, it essentially carves out areas exactly around training points where, yeah, if I would have asked any of you, I now query right besides this somewhat lonely blue point there in this the sea of yellow, just beside it, what color do you think should the predictor give? I think and I hope that all of you would have said yellow rather than blue, right? And regarded the blue one more as sort of like, okay, it's an accident, measurement error, noise, whatever. KNN at 1 doesn't do this. But we can, of course, crank K up. And for reasons that are completely unclear to me, in the book, they decided not to go for 9, as they did in chapter 3, but now they go for K is 10. Okay, but 10 and 9 are sufficiently close to one another, so the behavior is comparable. And as you can see, just as previously, with a sufficiently high, but not too high value of K, we can actually approximate a nonlinear decision boundary very well. In this particular case, what is the error that we get? I somehow don't have it in my notes, but it is low. It is low. I mean, it's not quite the 0.1304, but it is low. And you can all just eyeball this, of course. If we push K too high, so this is all hand plotted, so there we go. Then we essentially get the one single average over our data, right? I mean, and that is what we now get. So if we push it even further, then yeah, it doesn't give anything for any further information. It essentially becomes an average, nothing more than that. So K100 is definitely too high, right? I mean, so we don't want to use 100, we don't want to use 1, something that is small enough. You already know that I'm only going to tell you in chapter 5 how to choose K, but still to tease you a little bit further and to cover chapter 1 completely and fully, here we have both the training error that we do know how to compute, and in practice, I mean, and the testing error that in practice we cannot compute that easily, right? I mean, only if we would have the true or infinite data or the true model. As you can see on the training error, I mean, for this particular data set, this is a real data set that we're looking at. Higher values for K, or actually no, the lowest value for K looks really good on the training data. It is 1 and 0. This really, every time I look at it, literally every time I need to shift my brain. Like 1 is low and 0 is higher. Right hand side should be high in my brain. But if we now look at the orange curve, yeah, we want to have sort of a medium value of K, right? But from the green line, which we can compute, there is no signal where to get this. So, tricky problem. Okay, well, now finally, welcome back to November 11th. Now we're actually going to continue properly. Because all this KNN business, nice, but we don't know how to choose K, right? I mean, so the question you could ask, perhaps even should ask, why not just do linear regression, right? Because if we can find somehow like a line across the data that separates the blue from the yellow, then hey, why not use that somehow, right? It feels like we should be able to do that. And you're right. It actually can. If you code your samples, just like 0 and 1, for in this case green and red or green and orange, whatever it may be, then the output, let's say you will try to find a line that, depending on the output, will then either give a 1 in case it's red, or a value of 0 in case it's green. And if the data permits this, then we're done. It's perfect. And it's really just as simple as that, right? And I'll show you, I mean, why this also fails miserably in practice in a second, but let's now play pretend. Now, the problem is, the moment that we have more than 2 classes, let's say we have 3, then the simple linear regression trick starts to break down. Because somehow we would need to code, we need to give a number to each of the individual classes. And the whole point of classification is that we have just categories, right? They're not ordered per se. There's no distances between them, because then it's a regression problem. So that means that we can either say 0 is green, 1 is red, 2 is blue, but yeah, why not make 1 blue and 2 red, or any other permutation? They're all viable. And for each and every which one, you will get a different regressor, and basically there is no telling, no steering for how to make it actually work properly in that regard. You have to be ridiculously lucky to get the numbering right, and you're lucky enough that your data allows a linear classifier to begin with of this type. So basically don't use linear regression, definitely not for if you have multiple labels, more than two. However, linear regression is essentially the workhorse of, you could say, well, not all of classification, but for a very large part of advanced, between very big quotes. I mean, I'll have a short video of one of them, hopefully near the end. Hopefully we have time for that. That is really the workhorse behind a very large number of real-world classifiers being used right now. And the main trick is that we don't use linear regression directly. We apply a logistic function to it. And then, well, like snow for the sun, most, if not all, problems disappear. Because what do we get? Here we have the problem, right, with linear regression. We have balance, so how much the people already borrow, and what is then the probability of defaulting, right? So basically class mean if you default at the top, that's 1, right? We know these people defaulted, and at the bottom, then you have the people who did pay back or have not defaulted yet. I mean, I don't know how the data looks. And as you can see, with a straight line, it doesn't really model the probability that well, right? I mean, that's so it's a bit of a shitty model for this data. If we now simply apply a logistic function, remember that is just purely e to the power whatever you had, that entire thing divided by 1 plus e to the power whatever you had, and you're done, you get a very nice curve, as you see right here, between 0 and 1, and we can interpret its values as probabilities. Perfect. Very, very nice. And, well, we can also make this work now for multiple classes, because we can have these P of x's, and it's predicting one particular label. In this particular case is predicting that you will default. We can do this for each class label individually. And as long as we optimize overall, everything is fine and dandy, right? It's a purely pretty probability density function overall. Okay, so, well, what more can we do with this? Or why is this nice? Well, the first thing that is nice is that we can interpret this thing, right? So the first thing that's nice, okay, all values are sensible between 0 and 1, right? I mean, it's like we had previously, I didn't even comment on it, but what on earth if somebody has a balance below 500, what does a probability or minus something mean? Is this like, okay, it's like, well, they're gonna pay back extra? I don't know, right? I mean, it's a bit nonsense. Now all values are sensible, and we can interpret the formula that we have. It's not just applying a logistic, but what do we get? The odds ratio, this is what you get if you go to a betting office, right? You want to bet on horses or something like this, right? I mean, that's so you pay in 1, and then what's the ratio? It's 1 on 20, and that's essentially the odds ratio is this e to the power thing that we had. So we can interpret both this one in the numerator and in the denominator as the odds, right? So it's sort of a variant of the odds ratio. If we apply the logarithm on odds, and we have the log odds or the logit, then the e that we had in the in the odds disappears naturally. And hey, look, that looks remarkably like just a linear regression problem, doesn't it? And that is, of course, very, very convenient. As you will, I will repeat myself, but we will see that this allows us to fit this coefficients. Plus, after it's going to be a bit more complicated than we had before. But the good thing is that, well, you just need to understand how it roughly works. You don't need to do it by hand. And that's the good thing here. I promise you that. We have people who implemented this stuff for us. But the good thing is that after we have fitted it, all these things follow exactly the same intuitions that we had previously. So we can compute standard errors. We can compute confidence intervals. We can compute prediction intervals and all that good stuff, right? But now for classification. So, okay, nice. Yeah, so this is a bit of an aside, but I mean, it's also useful. On the interpretation, again, or maybe a step back, if we now increase x, so this is the univariate case that we have, if we increase it by 1, right, so we just add 1 to it, what does this mean? Well, we can interpret, because of what we have here, that beta 1, that will, so if we increase x by 1, then essentially we're adding 1 times beta 1 to the log odds ratio. It has a nonlinear effect on p of x because of the division, right? And that's this if we just unroll it back here. Whoa, what happened here? There it's still okay. Okay, here now it's also. Okay, it has a nonlinear effect over here. And if you now work it all the way back, if beta 1 is positive, then adding something to x will have a positive effect to the probability. And if beta 1 is negative, it will depress the probability overall. So we can interpret the coefficients quite easily, right? I mean, if you have a high value of beta, just like in linear regression, it will drive the probability up a lot. And if we have a negative value, well, it will drive it very much down. And if it's close to zero, it's zero, and well, that good stuff. Okay, how do we now fit it? Nobody pressed the panic button, right? I'm going to explain the general idea, and only a bit later, either in this lecture or next week, I'll give you an example, but just to give you the intuition of it. And I do not expect you at this stage to repeat every step that we do here, or overall what we'll be doing is we're going to be maximizing the likelihood rather than minimizing a mean squared error, because we don't really have an error. And because classifier just takes, okay, it's like either it gets it right or gets it wrong. That's a bit coarse-grained, right? I mean, we want to sort of make use of the information already embedded in our model to steer us, like what is now a good or a bad decision, right? How should we adjust our coefficients? Otherwise, we're just feeling around blindly in space, like what is it? The so many blind persons and the elephant. I forgot K in that. Good. The first thing that we can do is so we simply look at what is now the probability for each data point x given beta 0 and beta 1, right? The interpretation that we just saw, right? We can just plug it in. Then we have, through the previous formula, what we're going to have is essentially we have probabilities for x for each of the data points that we have, for each of the outputs. And so these are the ones where we actually get it right, sorry. So this is where y, the true value is 1, and we get it right. And this is where y is the true value is 0, and well, we get that right too, right? And naturally, because probability sum to 1, the higher this is, the better, right? I mean, the more cookies we got, so to speak. And the lower it is, I mean, the worse it is. Now, likelihood, directly maximizing likelihood is always a bit cumbersome, because all these products, and products are nice, but not if you don't want to do too many. However, by simply applying a logarithm, we all of a sudden get the log likelihood, which we still want to maximize, right? Nothing changed there. But essentially, we have two sums. And that is nice because those we can compute just completely independently, right? And we don't need to take a product. We don't have super large numbers to worry about with overflows and blah, blah, blah. So maximizing log likelihood is what we do in practice. Actually, many people prefer to minimize the negative log likelihood, right? Just by drawing a minus in front of it. It has no practical advantage so much in the computation, but the negative log likelihood is what it permits an information theoretic interpretation. If you take a logarithm to base 2, right, and only then the number that you're looking at is the number of bits that we would need to transmit the data, so the labels, right, under the model at hand. And of course, you want to minimize the number of bits because then the model is more and more informed. And well, that gives rise to a lot of nice tricks that we can put on how to regularize these models, how to penalize them for whether they become too complicated or not, right? This is why we typically look at negative log likelihood. Forget what I said last 2 minutes about negative log likelihoods. It's just we can put a minus in front of it, then you minimize it. Typically, in this lecture, we just maximize the log likelihood. How do we do this? Well, the nasty thing is, compared to previously in linear regression, where we could just some linear algebra, or in the univariate case, we can quite directly compute the coefficients. We have this nonlinearity that is going on. We have this squiggly shape that the logit function or the logistic function applies to it, right? So we don't really know exactly if we adjust beta naught by 0.1 up, what is going to happen with the probabilities. We can compute it, but for every adjustment, we will have to compute. Because beta naught and beta 1, they have a very strong interplay, right? I mean, previously, it was relatively easy. Beta naught was just the intercept, right? And right now, it's a bit more complicated. So we will still be using quite a bit of linear algebra in the end, but we need something in addition. And in practice, what we actually use is gradient descent and a nonlinear version of that. Let me give you very quickly, if I can, draw it. Normally I do it on the blackboard, but then I need to move the camera around a bit too much, so let's not do that. Let me try to do it like this. Okay. Black back, yes. Okay, let's see. Let's first draw with my finger. Let's see how good or bad this is going to be up. So we have, let's say we have just one beta. This is pretty bad. And this is going to be now my likelihood, something like this. We want to minimize the likelihood, right? Or maximize. What did we say? I want to minimize. Right now I want to minimize. It's going to, in general, if we just have one coefficient, right, which is not what we're looking at in linear regression or in logistic regression because we have two, but if we just have one, essentially what we're looking at is this. And I need to teach my monitor to not adjust the colors when I'm disable. Okay, now it's blue again. Essentially, we'll take a shape like this, which means that for a given value of beta, let's say we are here, right, over there, and we want to, well, go to the dip. I mean, it generally has this nice single minimum point where we want to arrive. But because these coefficients, here's only one drawn, right? I mean, I tricked you, and there's another one behind, but we'll deal with that one later. So we now want to adjust this beta such that we get as close as possible to this minimum over here. Now, how do we do this? Well, we can write out the formulas. We can set the derivative to 0, and then, well, okay, then we know in which direction we need to go, right? I mean, so we want to go, regardless, in this direction in this particular case. Drawing is horrible. I mean, it's even more horrible than if we would do it on the blackboard. But anyway, we want to go down in this particular case. So we want to follow the derivative. Now, suppose that we're now here, right? I mean, where I draw the spider web kind of thingy, you want to go down. How far do we want to go down? Because there's this interplay, right? I mean, if I jump too far towards the minimum, because there's other parameters to be estimated as well, and there's an interplay. If I move too much in this direction, then I'm going to screw up the entire model, right? Because all the others, they didn't have time to catch up yet, and they're like, okay, what the hell happened here? So we need to move sufficiently slowly. We need to follow the gradient, but sufficiently slowly. Now, the main trick that you do in Newton-Raphson is that you not just look at the sign of the derivative going down, right, the negative, but you now also look at the second derivative to see what is now the steepness at which we're going down. If we're at a super steep region, so let's suppose that we were here, over here, we want to take a bigger step than if we are already somewhere over here, right? So we have to look both at the first derivative and the second derivative. And we're going to apply some linear algebra on top of that. I'll show you in 10, 20 slides, something like this. So whether it's today or next week, I don't know. But this is the general idea. We are at the current point. We figure out the derivative, we figure out how steep is it, and we take a step to the minimum accordingly. Right? And then we go to the next variable, or the next coefficient, and we keep on doing this until after a number of iterations we're done. So rather than in the linear regression case, where we can jump in one go to the optimal result, right, after some painstaking linear algebra, right now we need to do this in multiple smaller steps, but we do know, we can guarantee, given the shape of this problem, that it will find the minimum, given enough times and small enough steps, which also means that you can screw it up massively if you don't do that. Okay. And like I said, people have implemented this for you, so you don't need to really worry about this. In the end, so the intercept has a special meaning. It is namely the probabilities that we fit under the beta 1, beta 2, beta 3, right? It's sort of like the catch-all. So it adjusts the total probabilities that we had back into probability space. Yeah? So it's essentially that everything nicely sums to 1. So it's essentially the proportion of ones, proportion of positive labels in your data. That's essentially what you get. So it is a relatively meaningless parameter, right? I mean, and sort of you get it for free. You don't need to worry about it. Similar like in linear regression, you also don't really care about the intercept because it's just a given, right? And if you would now shift your data around, right? What used to be x0, x equals 0, is now x minus 10, something like this. Well, yeah, the intercept will change, but the slope will not, right? You're typically more interested in the coefficients, the real coefficients, than in beta naught. Okay. Very short interlude, and then we go for a short break. We have now seen already with k-nearest neighbor classification and with linear regression-based classification, or whatever you want to call it, and now with logistic regression, two different classes of classifiers. In the one, and the left-hand side, oh, whoops, I need to make sure that I'm not using my pen. Yep. Yeah, so in the discriminative case, the one class of classifiers, we directly aim to estimate the class label G hat of an input point, right? So there is a true labeling function G, and we want to approximate, well, that labeling function, so we get G hat. On the other hand, what we just saw with logistic regression, we say, okay, you know what? There is a probabilistic way of assigning a label G to a data point X, where G is out of, for each of the classes, we have a different labeling probability. And what we're now trying to do is we try to get somehow a grip on the probability distribution. So we either have a labeling function or a probability distribution. Conceptually, these are similar yet different, right? It's really one of those type of similar but different. In the first, we directly get an estimate of the output, right? It's an apple, or it's a that, it's a such or so. In the second, in the generative case, well, we get probabilities, and we then need to make a decision which probability, so which label to give based on these probabilities. And typically you go for the highest probability, of course, right? So there's not so much difference in practice between these two classes. In the left-hand side, so the discriminative side, well, you just get the answer, that's that, and nothing else, right? And you might pry the method open to get some type of confidence, but some methods just refuse to give you that. They can just tell you, okay, no, it's an apple, that's that. So the only thing we can do is use a loss function. And well, then it really depends on your creativity, on how much information can you tease out. The right-hand side, in the generative case, we use not just the loss function, but also our model fitted already, right? The probabilities. So that's what we do with this gradient descent. We can't directly go to the lowest point because we have no clue where it is. We just know that it exists. So we kind of hop around at each step, improving our model until, well, we can't improve any further. So we leverage this. Slightly different interpretation. And what are you doing overall? You're either minimizing a loss function, or you're maximizing the likelihood, or minimizing the negative log likelihood. There you are. Right? Discriminative and generative classification in a nutshell. And literally every classification method I've ever encountered falls into either of these categories. Are they, in practice, really that truly different? Like I said, the first one you can often pry open and somehow interpret some confidence as sort of a probability, and there you are. And this, for example, what you also have in neural networks, which we'll see in the very last lecture. Those are not generative really, but just like we now did with linear regression and applying a logistic function, all of a sudden we can interpret these probabilities, even though linear regression does many things, but it doesn't give you probabilities, right? So this framework that you have here just gives you a way to think about methods and to, well, categorize them, to classify them if you wish. Good, let's take a break till, let's say, 12 minutes. Then on my clock it will be 15 past 5, and on that clock too. So well, see you in 12 minutes. And that it was going to be warmer. Good, okay, so back to logistic regression. How do we now use it? And this allows me immediately to answer also on the screen here one of the questions I just got in the break. When I said, if we add 1 unit to X, what does this mean? And indeed, that, I mean, I'm following the writing of the book, and they speak of units and stuff. In this particular example, where we're looking at, okay, given how much debt that you already have, how likely are you to default on your loan, right? The idea is, what if you would borrow €1 more? What does this do to your chances of defaulting, right, under the model? That's adding 1 unit to X in this particular case. So how does this look? If you have already borrowed €1,000, respectively 2,000, if we just fill this out in the model that we fitted through this gradient descent method, right? I told you don't have to worry about it. We magically did it behind the scenes. So these are the coefficients. We have beta naught is minus 10.65 and so on, and beta 1 is 0.0055. We plug this in, and what we get is that at a current depth of €1,000, I mean, the model says that you have a 0.00567 probability of defaulting. So well, you're pretty safe as an investment. If you have already borrowed 2,000, then, well, it looks a bit more bleak, right? I mean, I'm not going to give anybody money who already borrowed 2,000. Or at least that might not be so smart, right? Depending on how much risk you want to take. So effectively, if I increase the credit balance by €1, what do we get? So we have this 1,000 becomes 1,001. Hence, we have 0.005 in addition in the log odds. And yeah, essentially you can directly interpret the coefficient, in this case for balance, by the increase in probability. Or in the increase in log odds. And then computing, plugging in e to the power 0.0005, that then gives you the probability that you get in addition, right? So good. Okay, that is relatively straightforward, I would say. Can we, just like we did in linear regression, also include non-continuous attributes? Suppose that we have a discrete attribute. Is somebody a student or not, right? I have a room full of students in front of me. Yeah, by exactly doing the same trick as previously. We just create a dummy variable, right? I mean, student equals yes, which is true, which is 1 if you're a student and 0 if not, and so on and so forth. We can plug this in. Now, based on this model, so we have now 2 input cases. So I don't, and still the simple, very simple logistic regression where we just have 1 input variable, right? It's not multivariate yet. So this model is completely uninformed regarding how much you already borrowed, and now essentially gives out a prediction, gives out its estimate if somebody is a student, should you borrow their money, or if somebody is not a student. And as you see that for student, well, 0.00431 and for student no, 0.00429. This is not really good news for you. You're not going to get money. It is bad, right? So we can plug it in. Right? And actually the question where we actually want to go is this already. Oh, somehow it fell off the slide, quite literally, I think. Taking into account whether somebody is a student or not, in addition to how much they borrowed, that might make sense, right? If you make a lot of money and, well, you might have already borrowed a lot, but then regardless of whether you're a student, sure, we can probably borrow more. If you have borrowed a lot and are a student, okay, perhaps be a bit more careful. If you, make very little money, then regardless of whether you're a student or not, so there is interplay, right? So we really need to step away from the individual, for the univariate model to a multivariate one. Can we do that? Again, just like with linear regression, actually, the answer is relatively straightforward. Everything I've told you in the last half hour or so extends quite naturally to the multivariate case. Just like we call it multiple linear regression, right now we call it multiple logistic regression. Reasons are obvious. What we're now going to get is if we just look at the log odds here that we have, then if we now unroll it by just computing what are now as dpx's, how it is determined, this is just going to be beta naught plus beta 1 times x1 plus beta, and so on and so forth, up till beta p for xp. So this should be a subscript 1 for this x over there. And if we unroll it further, then for the probability, the direct probability for x is simply the e to the power of the whole linear regression thing and normalized accordingly. How to make predictions if you have the coefficients? Well, I don't need to tell you anything, right? It's just I can point to the slide. It's obvious. You just take the input values times the coefficients, put them together, e to the power of that value, and there you are. You get your probabilities. Yep. Good. So what do we now get? We see that in the previous model, where was it? Should point here. Oh, it goes a bit too fast. Here. So being a student, that adds a lot to the log odds, right? 0.4. That's quite a lot, right? And it's positive. Whether it is now positive or negative for the credit giving, let's ignore that, right? But it's high and it's positive. Here, all of a sudden, we have the multivariate model. Where do we have? So we have student is yes, so this is the first one. It's really small. It's really small. Actually, not the last one. This is so it's negative. It's negative and large. Sorry, somehow this is reordered. But I mean, student is just the 1, 0, so that's all the others are not 1. Minus 0.6. That feels a bit weird. That in the one model, it has a very positive, and the other one has a very negative effect, right? That's okay. What is actually going on here? Well, turns out if you look a little bit more closely in the data, that, well, surprise, surprise, students, well, they make less money, and hence, this is for American students, they love to use the credit cards. I hope that you're all a bit smarter in that regard, but hence they have relatively high drawing credits. So, but they also know that, hey, I don't have so much income, so they don't overdo it. So the baseline credit is relatively high, but they have things relatively under control. They know how to live with relatively little money. So in that sense, it's quite okay to borrow to a student, not just because they know how to survive with little money, but also, hey, there's a pretty big chance that after they're done with their studies, they're going to get a nice job and they can pay back. Whereas compared to somebody else who has a shitty job and not such bright prospects, if they have the same amount borrowed already, that looks much more bleak, right? So that's what you essentially see here. Students, even though the students that do default, they have a relatively high balance, but there's also a group with a relatively low balance. What essentially is going on is confounding. The story that I just told you, which seems also supported by the data, students know how to deal with relatively little money and so on and so forth, that confounds. So in a way, we have now all of a sudden a class in our data that can handle better than the others, relatively high drawing limit. If you do not allow your model to be informed of this, then you're going to draw the wrong conclusions. And if we only build a classifier, or logistic classifier in this particular case, just on studentship, okay, let's not give them money. But if you take into account all parameters, then actually it's not so bad. So you have some confounding, and in the multivariate case, you can tease this out. As I've also mentioned in the previous lectures, confounding is really, it's a beast that is completely unsolved. The moment that we do not have all the relevant variables, you can pray to the god of data science, but I mean that's your prayers will not be answered, because if the answer will not be in the data, right? There is actually something steering the process, right? If you do not know whether somebody is a student or not, but this actually is really important, and it's not in your data, there's nothing you can do. You will get a model that will steer you adrift, right? So be always aware that there can be confounding in your data, and some of this confounding can be hidden. So whenever you deploy a model, be it in a course, or be it especially in real life, really think hard, did we measure everything that might be relevant, right? Or might there be, oh, wait a second, we have an explanation for this subgroup. Because the moment you have, you're going to have a model that will be very biased and very unfair to a subgroup. And well, if you're the one who wants to make money out of your model, you're the one who's hurted, or hurted, the one who will be hurt. But if your model will make decisions for other people's lives, then yeah, well, you'll be liable, not me, because I told you about how to hidden confounding. Good. Let's see. This is just illustrating a little bit further. Let's not waste any time on this further. So how do we fit logistic regression models? Now that we've gone from the single case where I just drew the curve and we're just going to hops down, right? I already gave you the intuition. Let's see how to do this now for reals. I'm going to walk you through one example, and if you get lost, it is kind of okay for once in EML. And not the rest of EML, I mean, please don't get lost, but right now it's kind of okay. The details you will not find at all in the ISLR book. They literally say, okay, well, smart people build algorithms, use them. That's quite literally the quote. But, however, I have a room full of smart people in front of me, and these smart people can also look up into the ESL book, chapter 4.4. You do get the details. Still a little bit sparse, I have to admit, but still good. So yeah, what do? We have a general example here, right? So we step a little bit away from the whole how much did people borrow and whatnot. So I have two classes. So big G are my classes, and these are the values that I have, either 1 or 0. So we look at a binary classification problem, right? It's apple or an orange. The other thing that I have here at the top is the likelihood function. So curly L is typically used for likelihood. And I now have a theta here rather than a beta, because in that book they like theta and the other one they like beta. Luckily, the pronunciation is not so far apart, right? It's in a way the same. So here we have thetas. Theta is just a collection of betas. And what we're interested in is for each class K, so one of the G's, and a data point I, given the parameters, what is now the probability that the true class label indeed takes the value K, right? Is it an apple, is it an orange, given these input values and the parameters. In a binary classification problem, we are in luck because we don't need to build a classifier for the apple and a separate one for the orange, because, well, there's only two possible outcomes. So the moment that we have the probability for the 1, and we know that something has to be something, right? It's an apple or an orange. So if we just compute the probability for the 1, the other one is just 1 minus the probability we just computed. So this is what we have here, right? Probability for class 2, this is just 1 minus the first class. You can already see if we were to generalize this, then we don't need to build k classifiers, or we don't need to infer k distributions. We can always do just k minus 1, the last one we get for free. Okay, now, log likelihood, just applying logarithm on this entire thing and writing it out. Then we have this monster over here. And after a bit of rewriting, and I'm going to show you on the next slide what this looks like. So this may look spectacular, but actually it is not. We go over every individual point. We go for the positive labels, right? So if yi is truly 1, well, what do we get? We get the reward of the logarithm of the probability that, well, we got it right. So if we got it right, we get the amount, logarithm of the probability that we said it was right. In the ideal case, right, if we have the perfect classifier, the magic God-given classifier, then of course the probability for saying that it's an apple, right, for each time that we get something that looks like an apple, that should be 1. And the logarithm of 1 is 1, so we get the maximum score, right? So then we have 1 times 1. So then we really have a very high logarithm, or very high likelihood over here, log likelihood. And the same thing we do here, but in reverse. So if it is actually a 1, or if it is actually a 0, we should say 0, right? We should not say that it's a 1. That's what you do here. For each of the times that we should have said 0, how much probability mass did we accumulate there? Easy peasy, right? That looks more intimidating than it is. Okay, if we now rewrite this monster over here, and I'll show you in the next slide which are the steps, then we arrive at this one, which means that we now have simply the label yi, and we go over each data point. So for each of the labels, we simply have a vector beta. Yes, I'm mixing up the notation here like mad. On the left-hand side, I have theta, on the right-hand side, I have betas, because in linear regression, we've been talking about betas. I don't want to screw up the things too badly. Beta transposed times an input, well, that is just linear, that's what we're doing, right? That's what we have been doing. So that is essentially the probability before the whole log odds thing. And here we have the opposite, and then it looks a bit more involved, but it comes down to the same. Just need to do the one minus trick. And because it goes through a logarithm, we can't do this plainly. Okay, now, one thing that somehow, I don't know in which slide it fell overboard. But what we typically do so I know it is normally in my story, but I don't remember saying it, and I don't remember seeing it on the slides, so I don't know what happened. What we typically do in regression tasks in general, and hence also in logistic regression, we don't just take the data as is. We don't just take attribute x1, x2, x3, x4. We add a magic attribute at the very beginning, which we, for all practical purposes, may call x0, or just make that one x1 and all the rest just move forward. What is the value? What are the values for this magic attribute? It's 1. It's just 1. It's always 1. This allows, in many analyses, to get you a nice intercept, to get an average number of whatever the class label is. It allows for a very nice interpretation. It also fixes things if your input vector is all zeros and you want to have some baseline, just ones, just adding a column full of ones makes lots of problems go away. It's also what we do here typically. And this is essentially what this means, right? It has constant term 1. There is this special column x0, but not, which is just full of ones. Okay, so now how was the rewriting? I mean, it's really not that complicated. So we started with this one. So you get this much log probability mass for the positive labels and this much probability mass for the negative labels. Okay, if we now rewrite this probability into this logic function that we had previously, there we are, for each individually. Okay, now if we apply the logarithm, we have this one over here. So what is now a logarithm of something divided by something? Well, that's the logarithm of this minus the logarithm of that. It's just plain logarithms, right? I mean, that's no surprise there. Now, if I have a logarithm of this e to the power beta blah, 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 well, yeah, then depending on the base that I choose, e will just disappear. Both the logarithm and e disappears. So this is why I now here simply have the top term without a logarithm and without an e. Up, there we are. And the bottom term, I still do have, well, something that looks a little bit more scary. And on the right-hand side, I do exactly the same. Okay, and of course, log to 1 becomes 0. So okay, so what is the next step? Now we, let me see. Yeah. Wait, now I'm confusing myself. No, actually, no, it's now easy. Basically, so this is the linear algebra step. So here we explicitly still have coefficient. So this is this magic 0 coefficient, right? We did the intercept coefficient. This is beta. So the first coefficient, we have the second coefficient. Transpose, that doesn't do much if we have just a single one, and so on and so forth. We just rewrite this entire thing now in linear algebra notation. We just consider it a vector rather than making it explicit. A beta naught, right, and a beta 1 and so on and so forth. Just collapse them. Then we have two statements that are the same, and well, there we are. So very simple. Going back one slide, hence we can go from this full expression to something that is relatively handleable. Okay, so now we have a function here, this one we want to minimize or maximize. Now we want to maximize it. I'm so stuck in this information theoretic game, right? I always put minimize bits. So here we want to maximize. Okay, we want to maximize it. So the intuition from half an hour back is still exactly the same, except that we now have the game that we don't just necessarily have one parameter, we have multiple parameters. So we need to do this flip-flop game. We optimize the one and then the other, and we need to see how we slowly get to this minimum, respectively, maximum. How do we do this? We set the derivative for each of the parameters to 0, and we get an expression like this, right? So we do the derivative of L with respect to beta, okay, then we get this expression, okay, fine, we set it to 0, and we do this for each of the individual for the betas. So we don't get just one such an equation, but we get a batch of them. For historic reasons, these are called the score equations. P plus 1, well, why P plus 1? We have P predictors and we have the magic column, right? Sort of this intercept thing. Good. There's no non-linear effect. Well, the student example already showed you, so I don't need to explain this any further. So what we're now going to do, I'm going to skip this part specifically. We're just going to immediately go to the right-hand side. We're going to do this gradient descent approach. How do we do this? We want to find, at the current point, what is the derivative? So in which direction should we move? That's the first derivative. Up, so, and what we then want to do, so the new value of beta is going to be the old value of beta times the first derivative, and times, so minus the first derivative, that's the direction in which we currently want to go. And how big is the step that we want to take? This monster over here is the Hessian. That gives us essentially the second derivative. So just like in the curve that I drew, right? But now we can do it in many dimensions at the same time. I put it here in gray because unless you really, really want, I mean, I can explain it, but it's not really something that I care to explain because I do not require you to deeply understand this. I want you to understand the idea, gradient, and the steepness of the gradient. This is how we want to move. Hello, Gert. Hello. I was already wondering who that might be, but yeah. I could have called myself the owner of a very nice iPad pen. That's, but it said Smolka, and yeah, I don't know. I didn't really identify as a Smolka, so good. Okay, so this is here in gray, so this is just simply the Hessian matrix. You can write it out. I mean, it's not so exciting. If we now combine this, in the end, what do we get? We get, so this is the first, this is the second derivative. This thing we can analyze, this second derivative, as minus x transposed x with this w in the middle. This w, this is where the Hessian comes in, and that gives us essentially for each data point, how important is it? What is now the effect on the log likelihood? remember that for the multiple linear regression, we also looked at the Hessian. And why? Well, recall from last week, you have these points, and these nasty high leverage points that steer your linear regression line too far away, possibly too far away, that have a very high impact on the slope of the thing. You can identify them by looking at the diagonal of this Hessian, and those with a very high value, have a very high impact on the slope of your linear regressor, right? This is where we use the Hessian. We do exactly the same thing here, except that we don't look at the individual values. The Hessian gives us what is overall now the importance of each of the values. So what is the importance of a value? That gives us how steep is the slope. If all these values are high, we have a very steep slope, and we need to take a huge jump. If the values are relatively small, well, they don't have so much influence, we should take a small step, right? We're already quite deep into the ravine. That's the intuition that you should take away from the second derivative in this Hessian. How this then exactly works out, if you follow this, implement this, then well, you have your own Newton-Raphson optimization method. These days, nobody does this anymore. You just put it into PyTorch or whatnot. And that's, I leave it to you if you want to be one of those people or not. But in EML, I mean, it's fine. It's fine. Yeah. So one of the important things, though, is initialization. So it is concave. So depending on how you flop it, concave or convex. So in the end, as long as you take small enough steps, you will find the minimum, right? That's the nice thing of this problem formulation that we have here. Many other problems are non-linear and have a very difficult optimization landscape. There may be many, many local minima. This is a problem you don't have, as long as you take small enough steps. So where should you just start? Well, essentially any set of betas will suffice, right? I mean, because as long as you take your steps, you will get there. So 0 is fine. It's just, I mean, not essentially your guess is as good as mine of what might the eventual value be. If you go for 0, essentially what you're saying, well, I think that most of the predictors have a very low, so you hope, of course, that they have some, but relatively low influence. Whereas if you were to say, okay, I'm setting my betas to 100 million gazillion, yeah, unless you really think that is the true value, then probably your method will need to descend really, really a lot in order to get to values of 0.0055 as we've seen before, right? So hence 0 is typically a good start. You can, if you now go down your curve, once you get to the close to the minimum, some overshooting may return, which means that you're going to go bouncing back and forth around over the minimum, right? You don't really attain it. So your method doesn't really converge, and that's a bit nasty. Essentially, when this happens, when all of a sudden you see that your gradient, if it inverts, right? So here we're going negative. When we need to go left, no, right. This is right for, yeah, you need to go right. And all of a sudden, oh, now we need to go left again. Whenever this happens, you simply halve the step size. So you only take half the influence of the Hessian. And if you keep on doing this, I mean, so even if the next few steps you keep on overshooting, this is possible, right? I mean, but by halving all the time, in the end, right? I mean, in the end, I mean, of course, by keeping halving, you will go to 0. So you will get there. You will get there. The step sizes will become small enough. Can take a while, but still. Okay. Let me quickly see before I. Where did we do this? Let's try to find. I remember that I wanted to illustrate something with the slide. Where is this? Okay. Oh, okay. So they're here. So okay, yes. Okay. Now we go a little bit back. Somehow I skipped this. I did explain the whole minimization thing. Now, what is really nice is that under the hood, what we're doing is just linear regression. Also in the multiple optimization case, right? It's just some linear algebra, okay, but in the end, it's linear regression. We make exactly the same assumptions under the hood. There's a linear line that under a logistic transformation, okay, then it becomes probabilistic and everything, nice interpretation, but in the end, it's just a linear line under the hood. And the parameters of this linear line, these betas, they're still, under all the assumptions that we have, still Gaussian distributed. They should be, which allows us to do the standard error thing and the confidence interval thing and the prediction interval thing, right? I said this earlier, but we can still do this. This is really, really nice. So we have a method that we understand well. the theory side, and also performs well. We'll see that in a bit. I mean, perhaps not even today anymore, that it performs well. But I have, really numerically, but I hope the audio works. So I haven't tested whether the audio from my laptop now goes over the speakers, because it should over HDMI. But I can, so if it doesn't work, then you just have to look at the slides and press play, right? In the PDF, it also works. I mean, that I tested. And that, let me see. Awfully silent. It's too silent. No, damn it. Damn it. Okay, how can we get the audio to work? See, I have some minutes to spare, so I'm going to see if I can get the audio to work. It should work. With HDMI, stupid thing. Zuspieler. Is that me? Laptop? Might be, right? Just crank up the volume to max. I apologize in advance, but probably nothing is going to happen. But, come on. Here it's also on max. So. And here, wait, here else. Oh, yeah. Yes, very good. Okay, terrific. Good. This is logistic regression. It makes a lot of noise. It sounds really like a race car, right? I mean, it is super simple, but it is super impressive in the end, right? I mean, that's anybody who doesn't look outside will think it's a Ferrari, a Porsche, or whatnot, right? I mean, this is logistic regression. Deep learning, if you use it in classification with a softmax, is just logistic regression. Right, so those of you who already know a little bit what a deep net is and what a softmax is, you have some really complicated, you fit all your parameters, right, and all the tuning and all the engineering is fantastic. Then you have, here's where the input go, deep, lots of neurons. And then in the end, you want to see, okay, is it an apple or an orange? You have an output layer that draws, so the activities of each of these neurons go to, is it an apple or an orange? And what we now do, we do a softmax over this. What is a softmax? It's exactly a logistic regression, just what we did. We just apply this logarithm over a logistic function. So in the end, whatever the accumulated input that this neuron gets from a previous layer, and respectively for this one, it turns under this sigmoidal function just in the probability. That's what a softmax does. It is, in the end, a very nice way, deep learning, to learn these probability distributions under the hood. But after all, well, we just put it on a scooter, and it's just a lot of noise, right? But, okay, certain ways of estimating a distribution are better than others, right? And that, as much as I love to bash deep learning, and that it definitely does have its place. But just to illustrate that what you've just seen is really under the hood what drives most of the most powerful classifiers. Good. Oh, oops. Oh. Yeah, don't need to play it another time. No idea why it now worked the second time and not the first time. Good. This is going to be the first slide next week. Unless you say, no, please continue. We want to be home late. No, okay, good. Well, that maybe somebody on Zoom wants to be late. Well, no, doesn't seem to be the case either. Okay, I thank you very much for your attention. See you next week. Bye.